We took a look at a completely free motion system. And usually that doesn't really happen in real life, but there are systems to where there's a slight hindrance that occurs other than gravity. And what we're going to do is we're going to introduce a new factor or a new term into the equation that we just formulated. So remember, before we had this. So we had md2x dt squared equals negative kx, and that was just our basic free motion system. Well, now we have, for simple harmonic motion, we have this thing, and that's called a damping factor, or sometimes called a drag factor. Right? And essentially what that does is it's going to be some sort of factor that's going to either dampen, or in other words, lessen the velocity, or in some cases, if you wanted to, you could try to make something to where it would increase the velocity, although that really doesn't make much sense, because then you would just continuously get an increasing sort of relationship, as long as that's bigger than gravity, or that factor is bigger than gravity. So essentially what we're going to do is we're just going to throw in one more term, and we're going to see how that alters the system. So this is our new differential equation, and I want you to notice that it looks very similar to the previous, except now we have this middle term, this damping factor. Right? So the damping factor is going to be given to us, and it's usually a ratio of essentially how the relationship is with respect to the velocity, etc. So it'll be given to us in the problem most times. There's three different types of damping. The first case is where a system is called overdamped. And that's basically what we have, a system to where the damping factor is much larger than the spring constant. And eventually it's going to be a significant sort of force that's eventually going to hinder the motion of the system significantly. So usually in that type of system, it's like, if you can see in the picture below, in an overdamped system, we might have like a thick oil or something viscous that's going to significantly hinder the system. The critically damped type is the one where it's just on the cusp of overdamped and just on the cusp of overdamped. So in other words, if there was any less damping force, then we would have basically one of our oscillatory motions, right, where it goes up and down and up and down. All right, it's an extremely minor force, and it's going to take a while for the system to get down to the point to where it's asymptotic. And then we have this underdamped, to where this damping factor is small when we compare it to the spring constant. And essentially what that means is that it's small, there's going to be some oscillatory motion, and over time that oscillatory motion is going to eventually slow down. So think of that almost like a super high bouncing ball. When you drop it, and the only thing that's kind of resisting it is gravity in the air. And eventually what's going to happen is it's going to bounce like maybe 10 or 12 times, and eventually it'll come down, but it's going to take a little bit of time. Whereas if you drop something that doesn't bounce, like maybe a baseball or something, it's probably going to be like a dead thud, or it's just going to go down once, and that would be a more damped type of system. So that's what the damping factor does, and we can see a couple graphs here. And we're going to take a look at a couple examples of where we would see this sort of thing. So let's just start out with a pretty generic example. And we have a system that has a 4-pound weight. And it's attached to a spring whose constant is 2 pounds per foot. The system offers resistance to the motion of the weight numerically equivalent to the instantaneous velocity. So that's a new sort of thing that we haven't seen in the first two problems. The weight's released from a point 1 foot above equilibrium, and we have a downward velocity of 8 feet per second. We want to determine what type of damping is going on, create a model, graph the function, and then we're going to go ahead and determine where the weight passes through equilibrium, and then we're going to determine where the weight reaches extreme displacement. All right, so let's go ahead and first of all try to pick apart and try to maybe find K and M, etc. Now we know that we have our formula f equals ma, or f equals mg in this case. All right. Since we're in feet and pounds, g is going to be that 32. The force is going to be 4 pounds, so we get 4 equals m times 32, or in this case, 1/8 is going to be equal to m. We're going to hold on to that. The spring constant K is given to us immediately as 2 feet per pound. And then the system offers a resistance to the motion that's weight is numerically equivalent to the instantaneous velocity. All right, so remember, beta is the coefficient of the instantaneous velocity, dx dt. So in this case, beta is going to be equal to 1 because it's numerically equivalent. It's a factor of 1. So it's not half, not double, anything like that. We know that it's released from 1 foot above equilibrium, so x at 0 is equal to -1. And we have a downward velocity of 8 feet per second. So x prime is going to be equal to, x prime at 0 is 8. If we go back up to our formulas, we have B, M, K, M, and that's all we need. So let's determine what type of system we're looking at, first of all. So we need the relationship of B over 2M, or beta, excuse me, over 2M squared, and we're going to compare that to the spring constant K over M. And we're going to see if they're equal, less than, or greater than. So for beta, we have 1, 2 times the mass, which is 2 times an eighth squared, and K was 2, and M was 1/8. And what's the relationship between those? Well, we have 1 over a fourth squared, which is 16, 2 over an eighth, which is going to be 16. And by multivariable real analysis methods, 16 is indeed equal to 16. So what does that mean? We have a critically damped system. And it also asks us to be able to describe the motion that we expect. And we said that if the system's critically damped, that means that there's going to be some factor that's equal to the drag, or some sort of force that's going to be, or some sort of resistor that's going to be basically equivalent to our beta. So in this case, we should expect a motion that's going to not be oscillatory. And it's going to slowly approach the point asymptotic behavior. All right, so critically damped means, it's not going to bounce up and down and up and down and up and down, but it's going to be slow to come to rest. Okay, so it will eventually come to rest. All right, so let's see what happens though. All right, so now our next task is to be able to find the equation of motion. Right? Our formula, x double prime plus beta over m x prime plus k over m x is equal to 0. Now we already know that beta is 1, so we get x double prime plus 1 over. We know that m is an eighth. And we know that K is going to be 2. And if we simplify that just a little bit, we get a really nice equation. X double prime plus 8x prime plus 16x is equal to 0. It's almost like somebody made up this problem to make the numbers really nice. We can translate this now into a characteristic equation, m squared plus 8m plus 16 equals 0, and this factors as a perfect square trinomial, m plus 4 squared equals 0, and what we end up with is m1 equals m2 equals -4. And now we have a case 2 type of homogeneous differential. All right, so let's take a look and try to get to our basic solution. So our YC for this one is going to be x of t is going to be equal to c1e to the minus 4t plus c2t e to the minus 4t. All right, so remember for case 2, you just throw in a factor of t for however many different repeated roots that we have. All right. We're going to find the derivative, and we're going to have to use a product rule on this guy right here. And so x prime at t is going to be equal to, by chain rule, negative 4c1 e to the minus 4t. Chain rule, derivative of t is 1, so that's c2 e to the minus 4t. And then derivative of e to the minus 4t, we're going to have that negative 4, so we're going to get minus 4c2 t e to the minus 4t. All right. Now we can substitute the initial values back in, and going all the way back up, we have negative 1 and 8. So our system now becomes negative 1 and 8, respectively. Now, anytime we plug in a 0, anything with a coefficient of t is going to go away. All right, so we're going to hold on to this, but we have to remember that c2 is going to go away. So we could just say c1 times 1 plus c2 times 0. Or in other words, that means that negative 1 is equal to c1, which makes things really nice. Now we plug into the derivative, and it's a little bit more work. So we're going to have negative 4. We already found that c1 was negative 1, and that's going to be e to the 0, which is 1, plus c2 times 1. And then this minus 4c2t e to the minus 4t, that just goes away because we substitute 0 back in for t. So we already know negative 1 is equal to c1. And if we solve this, we get 8 equals 4 plus c2, which means that 4 is equal to c2. And so our equation of motion, x at t, is going to be the opposite of 1 e to the minus 4t plus 4t e to the minus 4t. All right, so we just plugged in for c1 and c2, and we got our solution. Right. What does that look like? Well, we kind of have an idea, right? But part C says graph the function and interpret the graph. All right, so let's go ahead in our calculators. We can graph this. All right, it shouldn't be too difficult. I'm going to go ahead and insert our graph. So here's our graph, and if we interpret the graph, not really much of a surprise, because what we notice is that we have this sort of behavior. Now again, just like we looked at the other graph, this doesn't matter, anything to the left of the y-axis, because that's when t is negative, and so we don't care about that. So basically, it says that we start below the equilibrium for this, all right, and then we go through and we just trace it. It's going to hit like this high point right here, right, somewhere around here. So I'm just going to circle this as a high point. All right, it crosses somewhere around here, like between 0.2 and 0.3 probably. All right, and then eventually it starts to fade. Okay, so it has like that sort of critically damped motion. So if I was going to interpret this, basically it reaches one optimal point, all right, and then eventually it tends to 0 slowly. All right. And so now we can answer the other questions. All right. And the other two questions is determine when the weight passes through equilibrium. Well, the weight passes through equilibrium when the position is equal to 0. All right. So equilibrium is right here. So we're just going to set this equal to 0. So we're going to say 0 equals minus e to the minus 4t plus 4t e to the minus 4t. All right? And then we can factor out, and this is part D by the way, we could easily factor out an e to the minus 4t to solve this. And what are we left with? Negative 1 plus 4t. Remember, this never reaches 0. All right, so it doesn't contribute anything to our solution. So that was never 0 because it's an e, right? Unless t is infinity, which doesn't matter. And clearly, this is going to be when t is equal to 1/4 of a second. And does that make sense? Well, let's go up to the graph. And we can clearly see that from the graph that we have this sort of point where it crosses the axis. And I bet you if we zoomed in there, that eventually it would intersect at 0.25 or 1/4. So certainly that does make sense. Finally, the last part of the question is determine when the weight reaches extreme displacement. And we know extreme displacement is the derivative. All right, so when does it reach the highest point? Well, we're going to find the derivative of the original, or I'm sorry, of our function. All right, so we're going to find x prime of t, right, and x prime of t is going to be our 4e to the minus 4t, and then we're going to have to use a product rule on this part right here. So it's going to be 4e to the 4t, or 4e to the minus 4t, and then minus 16, because we have this negative 4 times positive 4, so minus 16t e to the minus 4t. All right. And then finally, we just solve this out. We get 8e to the minus 4t minus 16e t e to the minus 4t. Just like we did before, we can factor out that e to the minus 4t. We can actually factor out an 8e to the minus 4t, and that's going to leave us with 1 minus 2t equals 0. Remember, extreme displacement occurs at the critical values, and this is going to give us that at 1/2 second. That's when it's going to reach the optimal value. All right, does that make sense? Well, right here is a half, and it certainly looks like that this might be a point right here to where we reach the optimal value somewhere within there. All right, if we wanted to, we could certainly go back and figure out what the optimal height is, but it just asks us when. Right. So hopefully this is an overview as to how the damping factor works and what this really does to the system. So now no longer do we have this oscillatory free motion behavior, but now we have it basically being governed by the velocity. We're going to take a look at one more example of this, and then we're going to move on to systems that are governed by some sort of external driver.